Hello, for today's video lecture we're going to be talking about solving systems of equations using matrices. So a system of equations is any set of related equations. It's going to be sharing some variables. A linear equation is any equation that consists only of simple constants and variables. So we can't have any logs, no exponents, no square roots, stuff like that. So just variables and constants. And an example of a system of linear equations is going to be the equilibrium equations from a static problem or the equations of motion from a dynamics problem. They're going to be sharing variables, but there's going to be a set of equations that go together. In all of these, we're going to, again, the key aspect is we have multiple equations that share some variables. And we want to solve those equations for the unknowns in the system. And so any system of linear equations can be rewritten as a single matrix equation to solve it. This is an alternative to solving everything just with algebra, kind of brute forcing your way through a number of equations. So how would we do that? So step number one is going to be rearrange all of the equations so that all the constants are on one side, where all the variables and coefficients are on the other side. So it's going to be useful to have everything in the same order as well. So if I've got a bunch of variables, I want to write them in the same order if possible. So here I've taken some equilibrium equations and I've got them just as I wrote them in the first place. First thing I want to do is kind of rearrange it. I've moved all of the constants, so this 8 and 16 I moved over to the right. All of the variables I left on the left side, and I've put them in the same order. So it's fax, fbx, and fay. So fax, fay, fbx is the order I chose for all of this. All right, so next step is we are going to rewrite this kind of reordered set of equations into two matrices. So we're going to first have the coefficient matrix, and this is going to be a n by n matrix where n needs to represent both the number of equations and number of variables that we have. So here we've got 3 equations, 3 variables. We need to make sure those things match. So I'm going to have 3 rows, 1 for each equation, and 3 columns, 1 for each variable. So fax has a coefficient of 1, so that goes in here. Fay doesn't exist in this second one, so I put a 0 in there. So anything where the variable does not exist in a given equation, just put in a 0. And fbx over here has a coefficient of 1, so that goes in here. So this represents the coefficients in that first equation for fax, fay, and fbx. Done the same thing for the second equation. So fay is the only variable in there, so it's 0 for fax and fbx. 1 for fay is my coefficient. And then down here, fax has a coefficient of 8, fay has a coefficient of 4, and fbx has a coefficient of 0 because it doesn't exist. All right, so I've taken all of those coefficients and put them into my coefficient matrix. I'm going to next put all of the unknowns into a vertical variable matrix. So you're going to basically kind of copy the order that you use here. So fax, fay, fbx, and this here, fax, fay, fbx, put them in a vertical matrix like that. This is our variable matrix, x, is what we're going to be solving for. We want to know what all those variables are equal to. And then finally, we're going to do the constants matrix on the left. So this is just simply the constants I have left over on the left-hand side of my equation. So 0, 8, 16, 0, 8, 16. All right, so this is a matrix equation that is equivalent to this system of equations. So if I multiplied this by this, I'd wind up with the kind of left-hand side of all of my equations, and then this matrix right here represents all the constants. All right, so I've got A times X is equal to B in terms of my matrix equation. Next, I need to solve that. So I want to solve A, X, and B. I want to solve this for X. So to solve for each of the variables, we need to divide both sides by A. So if I want to know what X equals to, I would do, if it was just a scalar equation, I'd say, all right, X is equal to B divided by A. So we're going to do this by multiplying both sides by the inverse of matrix A. So if I have inverse of A times A, that's going to be 1, or an identity matrix. And so on the left, I'm going to have the inverse of A times B, and that should be equal to all of those unknowns I'm trying to solve for. And so doing this by hand is difficult in large matrices. So you can do it by you can do an inverse in a 2x2 or a 3x3 without too much trouble. But if you've got like 5 equations, 5 unknowns, doing the inverse of a 5x5 matrix by hand is going to be very difficult. And so we're going to use computers to do these inverse matrices. We're not going to do them by hand. And in fact, if you kind of go and rely on something like Matlab or Wolfram Alpha, you're probably relying on a similar tactic here. So this is how computers are going to solve systems equations for you. So if we do put in the A matrix to something like Matlab, we can easily do an inverse, multiply it by B, and it'll spit out answers for us. All right, so why use matrix equations? There's two reasons we want to use matrix equations and computer programs to solve forces in trusses or other instances where I'd have large sets of equations. Number one, it's going to save us time. So solving 10 equations for 10 unknowns is going to take a lot of time with algebra. And if we are able to do it quicker with a computer tool, we would want to do that. Number two, if we make a small mistake, it's much easier to fix everything that's saved in code. So chances are 10 equations, 10 unknowns, somewhere you're going to miss a minus sign, you're going to misplace a decimal point. If you do everything in code, then it's going to be easier to go back and kind of redo the work. You just simply fix it, rerun the code, and you get your corrected answer in all of this. All right, so how do we do this in MATLAB? So we would use square brackets to denote the matrix. A comma is used to indicate the next element in the same row. A semicolon is used to indicate the next row. The inverse function takes the inverse of the matrix and use the star or asterisk to multiply the two matrices. So finally, work in a script file and save your work so you can easily correct any errors. All right, that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.